Imagine a sudden blackout of the global positioning system paralyzing urban arteries, forcing autonomous vehicles into emergency stops as they lose continuous satellite telemetry. Public logistics models suggest this loss of satellite navigation would trigger a cascading failure in global freight, reverting vessels to manual dead reckoning and stranding millions of tons of cargo. The most devastating impact of a GPS failure would be measured in microseconds. The global financial system relies on satellite signals for absolute timing synchronization. High-frequency trading algorithms depend on GPS-derived timestamps to ensure market fairness. Market analysts project that a prolonged failure could trigger trillions of dollars in erroneous automated trades, revealing the terrifying fragility of our modern economy. To sever this dangerous dependency, physicists are replacing orbiting satellites with the microscopic precision of atomic physics. The ultimate solution lies in developing GPS-free quantum navigation systems. These devices abandon external broadcast signals, relying instead on the fundamental properties of atoms. Harnessing quantum superposition, a principle of quantum mechanics where particles can exist in multiple states or paths simultaneously until measured, researchers at institutions like NIST are engineering extraordinarily sensitive quantum sensors. The profound promise of this quantum architecture is absolute resilience. Because a quantum navigation system measures internal inertial changes against the absolute constants of nature, it requires no external data link. A vehicle equipped with a quantum atomic clock and a quantum inertial sensor can determine its exact position entirely in the dark, immunizing critical infrastructure against the vulnerabilities of the sky. This pursuit of immunity is an urgent response to escalating disruptions. The fragility of classical satellite navigation is already being exploited through GPS spoofing, where malicious actors broadcast counterfeit signals. Public records from global aviation authorities document thousands of recent incidents where commercial flights were fed fabricated coordinates, abruptly showing them hundreds of miles off course and forcing pilots to abandon automated routing. The economic hemorrhage caused by localized signal failures provides a grim preview of a broader blackout. When maritime shipping routes are subjected to continuous location spoofing, vessels are forced to anchor entirely. Supply chain analysts estimate that intermittent GPS degradation costs the global maritime industry hundreds of millions of dollars annually, shattering the foundation of just-in-time delivery models. Resolving this macroeconomic threat requires an unprecedented pivot from the vast scale of global trade to the subatomic realm. The solution to securing vulnerable supply chains is currently being engineered at the scale of nanometers. This transition represents one of the most ambitious intersections of theoretical quantum physics and practical mechanical engineering, harnessing the bizarre behaviors of atoms for global mobility. The core of this transition involves taking the most delicate physical states known to science and forging them into robust navigational tools. Atoms are highly sensitive to the slightest environmental changes. The engineering challenge is to capture this extreme sensitivity to measure gravity and motion while isolating the quantum state from the violent vibrations of a moving vehicle. The ultimate engineering objective driving this scientific quest is the perfection of the inertial navigation system. Classical inertial systems use mechanical gyroscopes to calculate a vehicle's current position based on its movements. However, all classical inertial sensors suffer from a compounding error known as drift. To correct this drift, traditional systems must periodically reconnect with GPS, re-exposing themselves to external vulnerabilities. The goal of quantum navigation is to eliminate this drift entirely by tying internal measurements to the unchanging properties of the universe. by utilizing cold atom interferometry, a technique that uses the wave-like nature of ultra-cold atoms to measure inertial forces with extreme precision. Engineers aim to build a completely self-contained device capable of guiding a submarine across the Pacific Ocean for months, entirely blind to the sky. This pursuit of absolute internal measurement directly mirrors the legendary quest for longitude in the 18th century. Before the invention of accurate seagoing clocks, calculating east-west position often resulted in catastrophic shipwrecks. It was not until the English clockmaker John Harrison developed the marine chronometer in the 1760s, a precise mechanical clock that maintained accurate time at sea, that the crisis was definitively solved. Harrison's triumph established a fundamental truth of physics that remains the bedrock of modern navigation. Measuring space is inextricably linked to measuring time. To know exactly where you are on the Earth, you must know exactly what time it is relative to a fixed point. Modern navigation requires vehicles to carry an unbroken record of time, a principle now leaping from brass gears to quantum atomic states. To understand why a quantum alternative is desperately needed, one must dissect the inherently flawed architecture of the traditional global positioning system. Operated by the United States Space Force, the modern GPS constellation consists of over 30 satellites orbiting approximately 12,500 miles above the Earth. The true heart of this system is a collection of highly precise orbital atomic clocks acting as synchronized metronomes. When an autonomous vehicle attempts to find its location, it is not sending a signal up to space. It is simply listening. The receiver picks up the continuous time broadcasts from at least 4 different satellites. By calculating the microscopic differences in how long each signal took to travel from orbit, the device mathematically deduces its exact distance, operating as a precise space-based timing equation. However, this architectural reliance on a space-based broadcast introduces a critical, inescapable physical weakness. By the time a GPS signal travels 12,500 miles through the vacuum of space and pushes through atmospheric weather patterns, its power is drastically attenuated. Scientists frequently compare the strength of a GPS signal reaching the Earth's surface to the optical brightness of a 20-watt light bulb viewed from 10,000 miles away. Because the broadcast is so incredibly faint, it is terrifyingly easy to drown out. A commercially available radio jammer can easily overpower the satellite signals within a localized radius, plunging nearby receivers into a digital fog. Furthermore, physical obstructions like dense urban skyscrapers or deep natural canyons can block the line of sight, meaning the primary navigational nervous system of the modern world can be severed easily. Escaping this vulnerability requires a radical inversion of the current navigational paradigm. Instead of relying on a faint time signal broadcast from an atomic clock 20,000 kilometers in the sky, researchers must figure out how to bring the clock down to Earth. The imperative is to equip every critical vehicle, financial data center, and autonomous system with its own highly precise earthbound timekeeper. Achieving this localized precision is an immense scientific hurdle. The classical atomic clocks currently flying on GPS satellites are large, power-hungry, and require the pristine vacuum of space to operate efficiently. To create a truly independent GPS-free navigation system, scientists must invent an entirely new class of timekeeping. This necessity has sparked a fierce global race among physicists to develop portable quantum atomic clocks for moving vehicles. To understand why scientists are focused on miniaturizing these devices, one must look beyond the immediate demands of spatial movement. Precision timekeeping is the invisible bedrock upon which the entire architecture of modern digital infrastructure rests. Every routed data packet, cellular tower handoff, and synchronized power grid relies on an impeccably timed metronome to prevent data collisions. Without a universal temporal standard, communications would rapidly devolve into chaotic digital noise. Within the global financial system, this temporal foundation becomes even more critical. High-frequency trading algorithms execute complex transactions at the microsecond level, relying on an absolute, synchronized timestamp to determine the exact sequence of trades across international borders. When the timing reference is flawless, the digital economy flows efficiently, but the slightest disruption exposes a systemic vulnerability that threatens global markets. If a financial data center loses its synchronization by just a few milliseconds, the consequences cascade with devastating speed. A momentary drift can invalidate thousands of trades, trigger automated fail-safes that freeze market access, or allow predatory algorithms to exploit the latency. This microscopic discrepancy can potentially cost institutions millions of dollars in a fraction of a second, highlighting the severe economic danger of relying on easily disrupted orbital signals. This severe financial risk explains why major banking institutions and telecommunications conglomerates are funding next-generation research alongside national defense agencies. The goal is to install localized, highly stable quantum atomic clocks directly inside these data centers. By creating a decentralized, earthbound web of absolute time, the financial sector can remain completely immune to GPS spoofing or satellite failures, ensuring continuous operation regardless of the external environment. The epicenter of this temporal revolution is the highly controlled environment of the National Institute of Standards and Technology, or NIST, located in Boulder, Colorado. Inside these subterranean laboratories, shielded from the faintest seismic vibrations, physicists operate in a landscape dominated by fiber optic cables, heavy vacuum chambers, and precisely aligned mirrors. It is here that the foundational rules of measurement are being rewritten. Within these pristine spaces, researchers wear specialized gear to prevent even a stray microscopic particle of dust from disrupting the delicate optical tables. In recent years, scientists at this leading institution have pushed the absolute boundaries of measurement science, constructing massive experimental apparatuses that manipulate the fundamental properties of matter. Their meticulous work is redefining how humanity tracks the passage of a second. The crown jewel of this ongoing endeavor is the optical lattice clock. By firing multiple high-intensity laser beams into a pristine vacuum chamber, physicists create a standing wave of light, forming an invisible microscopic egg carton made entirely of electromagnetic energy. Thousands of ultra-cold strontium atoms are trapped within these optical wells, held perfectly still so their natural, high-frequency internal oscillations can be measured without the blurring effects of thermal motion. The precision achieved by this mechanism borders on the incomprehensible. A modern optical lattice clock ticks at optical frequencies, millions of times faster than the microwave frequencies used in traditional satellites. This results in an instrument so stable that it would not gain or lose a single second, even if it had been running continuously since the dawn of the universe 13.8 billion years ago. Yet mastering time is only half the battle in the quest for true spatial autonomy. For a deep-sea submarine navigating abyssal plains or a fleet of autonomous vehicles navigating a sprawling metropolis, knowing the exact time is useless without knowing the physical displacement from a starting point. Time and space are inextricably linked in the physics of navigation, and conquering one demands the immediate conquest of the other. To completely sever the cord from orbital satellites and achieve a truly GPS-free navigation system, scientists must translate this unprecedented atomic precision from the realm of stationary timekeeping into the dynamic world of physical movement. The challenge is to engineer sensors capable of measuring acceleration, rotation, and microscopic gravitational shifts with the exact same flawless accuracy as the optical lattice clock. For decades, the military and aerospace sectors have relied on classical inertial navigation systems, or INS, to track movement when external signals fail. These legacy systems utilize a finely machined arrangement of mechanical gyroscopes to detect rotation and accelerometers to measure changes in velocity. By continuously integrating these measurements, the onboard computer mathematically calculates the vehicle's current position based entirely on its last known location. However, these classical instruments possess a fatal flaw rooted in macroscopic physics. Microscopic imperfections in manufacturing, unavoidable mechanical friction between moving parts, and thermal sensor noise cause tiny errors in measurement that accumulate relentlessly over time. This compounding phenomenon, known as positional drift, means that an asset relying solely on classical INS will eventually lose its exact bearing, straying off course if it remains isolated for too long. Quantum mechanics offers a profound, elegant solution to this previously unsolvable mechanical degradation. By stripping away the spinning rotors and physical springs of classical sensors, physicists can replace flawed macroscopic components with the eternally unchanging, identical properties of individual atoms. This radical shift removes the mechanical friction that plagues classical systems, replacing physical wear and tear with the immutable laws of quantum physics. Because every atom of a specific isotope is exactly the same anywhere in the universe, it provides a perfect reference frame that never degrades or requires physical recalibration. Recent studies published in journals like Nature demonstrate that harnessing these atomic properties can theoretically eliminate positional drift entirely. This breakthrough offers a permanent, highly accurate navigational fix for autonomous vehicles forced to operate in the harshest environments on Earth. Unlocking this absolute reference frame requires leaving classical mechanics behind and entering the deeply counterintuitive quantum realm. The engineering focus must shift dramatically from the macroscopic machining of metal down to the delicate manipulation of individual atomic states. In this microscopic domain, the traditional boundaries between solid matter and undulating waves begin to blur, revealing a strange new physics that engineers can exploit for practical measurement. In 1924, physicist Louis de Broglie proposed that all matter exhibits wave-like properties, a foundational hypothesis that would eventually unlock a new paradigm of scientific measurement. Today, researchers are weaponizing this very concept, using the wave nature of matter to detect the faintest gravitational anomalies and the most minute shifts in physical momentum. This revolutionary approach effectively turns the fundamental building blocks of the universe into the ultimate navigational compass. The technological key to this transformation is a highly complex process known as cold atom interferometry. In a traditional optical interferometer, a beam of light is split, sent down two different physical paths, and then recombined. Scientists can then measure tiny differences in distance based on how the light waves overlap and interfere with one another, creating a distinct, readable pattern of light and dark bands. Cold atom interferometry performs this exact same trick, but instead of using massless photons of light, it uses physical atoms. By exploiting the quantum wave nature of matter, scientists can split the wave packet of a single atom, forcing it to travel along two separate physical trajectories simultaneously before recombining it. Because atoms possess mass, their resulting interference patterns are extraordinarily sensitive to inertial forces, turning them into ultra-sensitive, drift-free rulers for measuring acceleration and rotation. To harness atoms as ultra-precise navigational tools, scientists must first strip away their chaotic kinetic energy. This requires laser cooling, a deeply counterintuitive procedure pioneered by researchers at the National Institute of Standards and Technology in the late 20th century. In a room temperature environment, atoms ricochet at hundreds of meters per second, creating a blur of thermal noise that completely masks their delicate quantum states. To observe their wave-like nature, physicists fire precisely tuned lasers at a cloud of rubidium atoms from multiple directions. Instead of heating the matter, the photons systematically drain the atom's momentum. As the atoms absorb and re-emit these photons, they rapidly decelerate, dropping to temperatures just fractions of a degree above absolute zero, allowing their undulating quantum properties to finally and clearly emerge. Once chilled into this sluggish state, the atoms are manipulated using the principle of quantum superposition. In classical physics, an object can only travel along one trajectory at any given moment. However, a carefully calibrated laser pulse can place a single ultra-cold atom into a state where it occupies two distinct energy levels, forcing it to travel two separate physical paths simultaneously inside the vacuum chamber. This mind-bending reality forms the core engine of a quantum sensor. The split atom drifts through the device, with its two halves experiencing slightly different environmental conditions depending on external forces. If the vehicle carrying the sensor accelerates, rotates, or shifts its orientation, the two atomic paths are influenced in subtly different ways, allowing the atom to act as its own parallel control experiment. After the divided atom travels its dual paths, another laser pulse recombines the two halves into a single state. Because the atom functions as a wave, these recombining paths overlap and interact, creating an atomic interference pattern. Recent studies published in journals like Nature detail exactly how scientists extract highly precise navigational data from these complex patterns of constructive and destructive atomic interference. The resulting pattern is a highly detailed physical record of the forces the atom experienced while in superposition. By measuring the phase shift, the exact degree to which the recombined waves are out of alignment, physicists can calculate the precise acceleration that caused the disturbance. Even the most microscopic external forces alter the interference pattern predictably, turning the atom into an impossibly delicate seismograph for motion. Reading these atomic interference patterns delivers a leap in navigational sensitivity that completely dwarfs classical technology. Because the measurement relies on the fundamental unchanging properties of a specific element, the resulting data is absolute. While classical accelerometers rely on springs, masses, and electrical resistance that degrade or warp with temperature changes, a rubidium atom remains perfectly stable, providing an unvarying standard of physical measurement. This absolute atomic stability effectively eliminates the mechanical drift that constantly plagues traditional inertial navigation systems. While a standard aircraft gyroscope might accumulate hundreds of meters of positional error over a few hours of flight, a quantum sensor theoretically maintains its pinpoint accuracy indefinitely. By anchoring measurements directly to quantum mechanics, scientists have engineered a navigational compass that never loses its true north. Translating the abstract physics of cold atom interferometry into tangible devices has led researchers at leading aerospace laboratories to create the quantum gyroscope. In these highly specialized instruments, the superposed atomic paths are forced to enclose a physical area, creating a continuous loop. As the gyroscope rotates, the atomic wave traveling in the direction of rotation covers a slightly longer distance than its counterpart. This minute difference in travel distance creates a distinct phase shift in the final interference pattern, allowing the system to calculate the vehicle's rotation with extraordinary precision. Unlike optical gyroscopes that bounce light through fiber optic coils, quantum gyroscopes use atoms with mass, making them exponentially more sensitive. A vehicle equipped with this technology can track its exact pitch, yaw, and roll without external references. Beyond measuring rotation and acceleration, cold atom interferometry is revolutionizing our ability to map the Earth itself through quantum gravimeters. Because atoms have mass, their wave functions are profoundly sensitive to the planet's gravitational pull. In 2022, researchers at the University of Birmingham demonstrated a portable quantum gravimeter in the field, using superposed atoms to detect subtle variations in the density of the ground. As the sensor passes over different geological features, the local gravitational pull fluctuates. A dense deposit of iron ore exerts a slightly stronger pull than a subterranean cavern or a buried utility pipe. The quantum gravimeter registers these minute changes by reading the altered interference patterns of its falling atoms, allowing scientists to create an unjammable topographical map charted entirely by underground mass density. This breakthrough in subterranean gravity mapping introduces a radical new procedure known as gravity matching navigation. If a vehicle possesses a highly accurate, pre-recorded map of the Earth's gravitational field, it no longer needs external satellite signals to determine its location. Instead, it continuously measures the gravitational pull directly beneath it using an onboard quantum gravimeter, comparing real-time readings against the stored digital database. By finding the exact match between the real-time sensor data and the pre-recorded map, the vehicle's computer pinpoints its location on the globe with astonishing accuracy. Because the Earth's gravitational field is a permanent, passive physical feature, it cannot be jammed, spoofed, or destroyed. Gravity matching navigation entirely bypasses the global positioning system, offering a fail-safe method of pathfinding that operates securely in any weather condition. The transition of these quantum sensors from immense, room-sized laboratory experiments into deployable technology is rapidly accelerating, shifting focus toward immediate commercial applications. Self-driving cars, delivery drones, and automated freight trucks require continuous, millimeter-perfect positioning data to operate safely. The civilian transport sector is rapidly realizing that relying solely on fragile satellite signals is an unsustainable systemic risk for the future of autonomous networks. As engineers work tirelessly to miniaturize cold atom interferometers, the automotive industry aims to integrate quantum gyroscopes and gravimeters directly into the chassis of civilian vehicles. This integration promises a continuous stream of uncorrupted motion and location data regardless of external conditions. Building a localized, independent navigation suite serves as the ultimate safety net for the artificial intelligence systems driving the vehicles of tomorrow. The urgency for this technology crystallizes when examining the volatile operating environment of autonomous vehicles navigating complex urban landscapes. Current self-driving technology relies heavily on the global positioning system, but city centers routinely create severe satellite dead zones. When a vehicle enters an urban canyon flanked by towering skyscrapers, the physical line of sight to orbiting satellites is instantly and completely blocked by steel and glass. Tunnels, subterranean parking garages, and multi-level highway interchanges present even more absolute barriers, plunging the autonomous system into a total navigation blackout. In these high-risk scenarios, classical internal sensors must take over immediately. If those traditional sensors drift even a few meters, a self-driving car could easily misjudge a lane boundary or an intersection. In a densely populated city, absolute internal positioning becomes a critical requirement for survival. By integrating onboard quantum sensors into vehicle architectures, researchers at leading institutions have demonstrated a definitive solution to these navigation blackouts. Recent studies published in journals like Nature highlight how a quantum inertial measurement unit maintains millimeter-perfect positioning through the deepest urban dead zones. Unlike traditional accelerometers that accumulate errors within seconds, a quantum system referencing the absolute properties of cold atoms remains flawlessly anchored to reality. This creates a continuous fail-safe positioning network for autonomous systems, effectively eliminating the danger of signal loss. When a self-driving car equipped with a quantum gyroscope loses its connection to orbiting satellites, the internal system seamlessly carries the navigational load without a fraction of a millimeter of drift. It is a technological leap that unlocks the full, uncompromised potential of autonomous vehicles, transforming a fragile dependency into absolute self-reliance. The implications of this unshakable accuracy extend far beyond individual passenger vehicles, promising to secure the entire global logistics network. Commercial shipping fleets and autonomous drone delivery systems currently operate under the constant looming threat of signal disruption, where localized outages can paralyze regional supply chains. In recent years, widespread spoofing attacks in international waters have caused commercial vessels to report their locations miles inland, exposing the profound fragility of maritime trade. Implementing fail-safe navigation for commercial shipping and logistics introduces a profound sense of security to a vulnerable global economy. A maritime cargo ship, guided by cold atom interferometry, becomes completely immune to malicious spoofing by state or non-state actors, navigating purely by unalterable quantum mechanics. For the operators managing billions of dollars in global freight, this technology offers the ultimate peace of mind, an unbreakable supply chain that cannot be blinded, misdirected, or digitally hijacked. While civilian logistics seek economic efficiency and safety, national security agencies view GPS-independent navigation through an urgent lens. The strategic defense imperative dictates that relying on a fragile, easily jammed satellite constellation during a major conflict is a catastrophic vulnerability. Consequently, military planners have initiated a massive pivot, recognizing that the ability to navigate without external signals is no longer just a tactical advantage, but a matter of absolute survival. This realization has driven the military prioritization of GPS-denied navigation to the very top of global defense agendas. In an era where electronic warfare can instantly blind a fleet's traditional sensors, possessing an internal GPS-free compass becomes the defining factor in strategic deterrence. The modern battlefield demands systems that can operate in complete digital darkness, forcing defense departments to aggressively pursue the quantum alternative. Nowhere is this requirement more absolute than in the extreme, unforgiving environment of the deep ocean. Consider the operational reality of a nuclear submarine, a vessel designed to remain submerged and undetected for months at a time. Beneath hundreds of feet of crushing, conductive salt water, radio frequency signals from navigation satellites simply do not penetrate, plunging the crew into total navigational isolation. In this silent abyss, submerged navigation without satellite access currently relies on highly sophisticated, yet fundamentally flawed, mechanical and optical gyroscopes. Over weeks of silent running, the microscopic friction and mechanical imperfections in these classical systems inevitably cause the submarine's calculated position to drift. To correct this error, the vessel must eventually surface to catch a satellite signal, a highly dangerous maneuver that instantly compromises its stealth and exposes it to hostile detection. To solve this critical vulnerability, defense organizations like DARPA have become the primary financial engines driving quantum navigation forward. Through initiatives aimed at accelerating atomic physics, a massive influx of defense funding and public contracts is rapidly pushing quantum sensors out of the theoretical realm. By weaponizing their budgets, these agencies are attempting to compress decades of standard academic research into a few short years of applied engineering. This aggressive military quantum investment is reshaping the scientific landscape, funding specialized laboratories and private defense contractors to achieve what was once thought impossible. The public budget priorities clearly telegraph the urgency of the mission. Whoever successfully deploys the first unjammable quantum navigation system will hold an insurmountable strategic edge. It is a modern space race, but instead of looking up to the stars, the competitors are looking inward to the behavior of supercooled atoms. Yet, despite the immense funding and clear theoretical pathways, scientists face a massive physical engineering reality that threatens to ground the entire endeavor. The current physical footprint of quantum sensors is staggeringly large, often requiring environments that resemble small factories rather than portable devices. A highly accurate quantum gravimeter, gyroscope, or atomic clock currently operating at institutions like NIST typically takes up an entire room, demanding rigid stability and immense power to function. These laboratory setups are sprawling labyrinths of technology, filled with complex arrays of lasers, precisely aligned mirrors, and bulky ultra-high vacuum chambers. They require heavy magnetic shielding to block out the Earth's ambient interference and massive cooling systems to keep atomic clouds near absolute zero. While these room-sized instruments can measure gravity and motion with unprecedented sensitivity, they are entirely useless to a moving vehicle, a flying drone, or a submerged submarine. This stark contrast between laboratory success and field deployment introduces the defining challenge for the entire quantum industry: the swap constraint. In aerospace engineering, SWAP stands for size, weight, and power, representing the ruthless physical limits imposed on any technology meant to leave a building. A navigation system must be small enough to fit inside a missile, light enough to be carried by a drone, and efficient enough to run on a standard battery. The consequence of failing to drastically reduce the swap footprint is absolute. The technology will remain a brilliant but trapped laboratory curiosity. If engineers cannot shrink these room-sized laser arrays and vacuum chambers down to a portable form factor, quantum navigation will never reach the consumer market or the battlefield. Overcoming this barrier requires a fundamental reimagining of how quantum hardware is constructed, moving from bespoke, hand-tuned instruments to mass-produced, miniaturized components. To achieve this, researchers at facilities like Sandia National Laboratories are engaged in the meticulous engineering process of shrinking the quantum architecture. They are pioneering the miniaturization of vacuum chambers, replacing bulky metal enclosures with sleek, micro-machined glass cells no larger than a matchbox. Inside these tiny sealed environments, they must still maintain the ultra-high vacuum required to trap and cool atoms, a feat of materials science that borders on the miraculous. Simultaneously, the engineering teams are tackling the complex task of stabilizing the lasers required for cold atom interferometry. Moving from delicate tabletop experiments to robust, shoebox-sized prototypes means replacing sensitive optical lenses with ruggedized, solid-state alternatives. Every millimeter of space saved and every watt of power conserved brings the technology one step closer to being bolted into the chassis of a commercial vehicle. The most critical breakthrough enabling this future portability is the development of photonic integrated circuits. Much like how the invention of the microchip revolutionized computing by shrinking room-sized vacuum tube mainframes into pocket-sized smartphones, photonic chips are poised to revolutionize quantum sensing. Instead of routing electricity through silicon pathways, these advanced circuits route actual particles of light, guiding lasers through microscopic channels etched directly into a wafer. By replacing sprawling, vibration-sensitive laser arrays with these flat, microscopic chips, engineers can drastically reduce the size, weight, and power consumption of the entire system. Photonic integrated circuits allow the complex optical dances required to cool and manipulate atoms to occur within an area smaller than a postage stamp. It is a necessary and profound leap forward, providing the exact technological bridge required to carry quantum navigation out of the laboratory and into the moving world. Even with photonic circuits shrinking the hardware, the fundamental physics of cold atom interferometry presents a daunting obstacle. the extreme fragility of the quantum state itself. To measure acceleration, atoms must be placed into a state of quantum superposition, behaving as waves rather than particles. This delicate wave-like behavior, known as quantum coherence, is notoriously difficult to sustain outside the perfectly controlled conditions of a laboratory. The battle to maintain this coherence in a dynamic environment is a formidable challenge. Researchers at institutions like the Massachusetts Institute of Technology have documented the immense difficulty of keeping the atomic wave function intact while a sensor is in motion. A single jolt from a pothole or a sudden shift in atmospheric pressure is enough to collapse the superposition prematurely, destroying the interference pattern. This vulnerability places delicate quantum physics directly at odds with the harsh realities of an operational environment. Inside a moving vehicle or an aircraft, the sensor is subjected to a chaotic symphony of environmental noise. Severe mechanical vibrations, rapid temperature swings, and fluctuating electromagnetic fields from the vehicle's own engines all conspire to disrupt the precisely choreographed dance of the laser-cooled atoms. Field tests aboard naval ships and research aircraft vividly illustrate this threat. The ambient vibrations of a ship's hull or the acoustic roar of jet engines can introduce overwhelming interference, masking the subtle inertial shifts the quantum sensor is trying to detect. If the atoms are jostled out of their ultra-cold, perfectly aligned state by even a fraction of a degree, the resulting measurement becomes meaningless. Overcoming this environmental chaos requires a massive leap in engineering, transforming a sensitive scientific instrument into ruggedized field technology. To shield the quantum core, engineers encase the vacuum chambers in advanced active vibration isolation systems, which use counterforces to cancel out mechanical shocks in real time. Simultaneously, multi-layered magnetic shielding is deployed to block out erratic electromagnetic interference. This triumph of engineering is already yielding tangible results. Recent studies published in journals like Nature Communications detail the successful deployment of ruggedized quantum gravimeters on moving marine vessels, capable of mapping the seafloor despite the constant pitch and roll of ocean waves. This evolution from a fragile laboratory curiosity to a hardened, deployable sensor marks a crucial turning point. With the foundational physics proven and the pathway to ruggedization clearly established, the narrative of quantum navigation is shifting rapidly from academic research to aggressive commercialization. The engineering hurdles that once seemed insurmountable are now viewed as solvable problems, igniting a fierce competition to shrink, stabilize, and mass-produce these systems. A vibrant ecosystem of specialized startups is spinning out of university physics departments, racing to capture what is projected to be a massive nascent market. These emerging companies are entirely focused on translating complex interferometry and laser cooling techniques into viable, off-the-shelf commercial products, packaging quantum phenomena into a black box for shipping conglomerates and automotive manufacturers. This corporate race is fueled by an unprecedented influx of venture capital. Financial markets have recognized the immense vulnerability of the global economy to GPS spoofing and signal loss, making the promise of a self-contained navigation system highly lucrative. Hundreds of millions of dollars are now pouring into the quantum sensing sector, driving rapid iteration. Public market data and venture capital trends reveal a targeted financial strategy. Investors are betting heavily on a post-GPS future. This capital allows startups to bypass the traditional academic development cycle, funding the immediate construction of advanced prototyping facilities and automated manufacturing lines. Market analysts project the quantum sensor industry to grow exponentially as the technology matures. Yet, the sheer complexity of quantum technology means private startups cannot navigate this transition alone. The current landscape is defined by deep public-private partnerships that bridge the gap between theoretical research and industrial manufacturing. Emerging tech firms are forging alliances with established defense contractors who possess decades of experience building ruggedized hardware for extreme environments. Crucially, these private consortiums work in tandem with national research institutions. Organizations like the National Institute of Standards and Technology provide the foundational metrology and rigorous testing facilities required to validate these early prototypes. By combining the agile innovation of startups, the manufacturing muscle of aerospace giants, and the scientific rigor of government labs, this ecosystem accelerates development. Despite this rapid acceleration, the immediate future of navigation will not be a sudden replacement of existing technology, but a strategic integration. The realistic near-term roadmap centers on a hybrid solution, pairing traditional, classical, inertial navigation systems with cutting-edge quantum sensors. In this configuration, the two technologies compensate for each other's inherent weaknesses. In practice, classical mechanical gyroscopes handle the high-frequency, split-second movements of a vehicle, providing continuous, real-time data. Meanwhile, the quantum sensor acts as an absolute reference point, periodically taking an ultra-precise measurement to correct the inevitable drift of the classical components. Industry white papers outline this exact architecture, demonstrating how a hybrid system maintains pinpoint accuracy without pinging a satellite. Based on this hybrid approach, a clear industry consensus is forming around the projected timeline for commercial rollout. The initial wave of adoption is expected within the current decade, primarily targeting specialized, high-stakes sectors where the cost of GPS failure is catastrophic. Military submarines, deep-sea exploration vessels, and long-haul commercial aircraft will be the first to integrate these systems. Following this initial deployment, the technology is expected to follow the familiar trajectory of miniaturization and cost reduction. As manufacturing techniques improve, these sensors will gradually trickle down to commercial shipping fleets and eventually to the consumer market. A world where everyday autonomous vehicles navigate complex cityscapes with absolute certainty is no longer a distant dream, but a scheduled engineering milestone. However, the ability to track physical movement through three-dimensional space is only one facet of this technological revolution. The fundamental quantum phenomena that allow a cold atom interferometer to measure gravity and acceleration are the exact same principles used to measure the passage of time. The quest to build the ultimate gyroscope is inextricably linked to building the ultimate clock. This dual-use nature of quantum sensors broadens the scope of their impact far beyond the physical routing of ships and vehicles. As researchers at the National Institute of Standards and Technology have demonstrated, miniaturized quantum atomic clocks offer a level of temporal precision that rivals their navigational capabilities. This realization shifts the narrative to the invisible digital infrastructure that underpins modern society. The invisible architecture of modern telecommunications relies entirely on a heartbeat broadcast from space. As global networks transition to 5G and lay the groundwork for future 6G infrastructure, massive data volumes require microsecond-level synchronization. Without this precise timing, data packets collide. Currently, this synchronization relies almost exclusively on the global positioning system, creating a single point of failure that a fully GPS-free architecture must solve. Telecommunications engineers recognize that a localized GPS jamming event or a severe solar storm could effectively blind regional network switches. The mobile internet remains tethered to a fragile radio signal traveling 12,000 miles through the atmosphere. To sever this dependency, the industry requires a ground-based alternative matching satellite-derived time. The solution lies in integrating miniature quantum atomic clocks directly into the terrestrial network. Research at institutions like the National Institute of Standards and Technology, or NIST, is focused on developing chip-scale atomic clocks specifically for this purpose. Telecom operators can install these devices inside regional data centers, generating a localized pulse perfectly synchronized even if the sky goes dark. Installing these systems requires careful calibration to ensure the quantum state remains stable amidst the thermal fluctuations of a busy server room. Technicians fiber link these localized clocks to create a distributed mesh network, allowing neighboring nodes to continuously correct microscopic drift. This procedural shift immunizes the data stream against external signal disruption. This localized quantum timing directly ensures the resilience of financial markets, averting the catastrophic desynchronization that would freeze high-frequency trading platforms the moment satellite signals fail. In the global financial sector, trades execute in fractions of a millisecond. A ground-based quantum clock network guarantees these transaction ledgers remain perfectly aligned across global exchanges. By removing reliance on a vulnerable space-based broadcast, financial institutions eliminate the risk of a coordinated jamming attack, artificially inducing a market crash. The consequence is a fortified economic infrastructure where billions of dollars move securely, anchored by quantum mechanics. This shift provides an ironclad guarantee of temporal accuracy. Beyond data and capital, ultra-precise timing is required to manage the physical delivery of electricity. Modern power grids operate as massive, interconnected machines, balancing generation and consumption in real time. As utility companies integrate unpredictable renewable energy sources, phase measurement units require microsecond synchronization to reroute power before a local fault cascades into a widespread blackout. Currently, these grid monitors depend entirely on GPS signals to align their data across thousands of miles of transmission lines. By deploying quantum atomic clocks at critical substations, operators establish a highly secure, autonomous timing system. This ensures the alternating current remains perfectly in phase, allowing automated systems to compensate for sudden power drops without risking failure. This widespread deployment across telecommunications, finance, and energy sectors marks a monumental geopolitical shift in how critical infrastructure is managed. For decades, the global standard of time has been centralized, controlled by a handful of nations operating satellite constellations. The transition to a decentralized network of quantum clocks replaces a vulnerable broadcast with a robust, distributed web of autonomous timekeepers. Nations and corporations are no longer beholden to the operational status of foreign satellites to keep their internal systems running. This decentralization of time fundamentally enhances national security and economic sovereignty, neutralizing the threat of orbital warfare as a vector for infrastructure collapse. Humanity is building a highly resilient technological ecosystem embedded directly into the terrestrial foundations of society, essential for supporting fleets of autonomous vehicles. Yet, while quantum atomic clocks secure digital and electrical networks, the exact same underlying physics is simultaneously unlocking a radically different capability. The extreme sensitivity of cold atom interferometry is not limited to measuring time. When these quantum sensors are calibrated to detect the subtle pull of gravity, they transition from navigation instruments into unprecedented tools for geophysical monitoring. Instead of looking up to satellites for guidance, scientists are now using quantum gravimeters to look straight down, peering deeply into the interior of the planet. Because the Earth's density varies beneath the surface, the local gravitational field fluctuates in minute, predictable ways. By mapping these microscopic variations, researchers are essentially developing a new way to X-ray the Earth. A quantum gravimeter operates by dropping a cloud of supercooled atoms in a vacuum chamber and measuring exactly how fast they fall, a rate dictated entirely by the mass of the material beneath the sensor. Because water is less dense than solid rock, an underground aquifer exerts a slightly weaker gravitational pull. As that aquifer depletes, the quantum sensor detects a corresponding drop in the local gravitational field. This capability allows hydrologists to track the depletion and recharge rates of crucial groundwater reserves with centimeter-level accuracy from the surface. Similarly, geologists deploy these sensors around active volcanoes to monitor the movement of magma chambers deep underground. Civil engineers also utilize this technology to identify hidden subterranean voids, anticipating sinkholes before they swallow building foundations. The immediate commercial value of this geological X-ray has sparked intense investment from the mining and energy sectors. Traditionally, locating dense mineral deposits or subterranean oil reserves required extensive, invasive, and costly exploratory drilling. Now, surveying teams mount ruggedized quantum gravimeters onto drones, sweeping across vast tracts of land to map the subsurface density in high resolution. As the aircraft flies over a hidden deposit of dense iron ore or a lighter pocket of natural gas, the quantum sensor records microscopic gravitational anomalies. Software algorithms then translate this raw interference data into a three-dimensional map of the subterranean landscape. This non-invasive procedure allows extraction companies to pinpoint exact drilling locations, drastically reducing the financial risk of blind exploration. This hyper-accurate mapping capability is actively disrupting traditional surveying industries, rendering decades-old geological maps obsolete overnight. Companies equipped with quantum gravimetry hold a massive competitive advantage, capable of identifying valuable deposits that classical instruments simply cannot detect. The economic ripple effects extend directly into global commodities markets, where predictive data regarding accessible groundwater and hydrocarbon reserves shift valuations. By providing an unforgeable ledger of the Earth's hidden inventory, quantum sensing eliminates the guesswork that has historically driven resource speculation. Commodities traders and national resource ministries increasingly rely on this quantum-derived data to forecast long-term supply chains and adjust economic strategies. Ultimately, the ability to see through solid rock transforms subterranean uncertainty into quantifiable data, reshaping the global resource economy. Beyond the immediate disruption of global commodities markets, researchers at the National Institute of Standards and Technology are harnessing these hypersensitive instruments to probe the fundamental laws of physics. The transition from mapping subterranean aquifers to questioning the fabric of the universe requires only a shift in the scale of observation. Where a commercial gravimeter detects the mass of an iron ore deposit, a laboratory-grade quantum sensor detects the minuscule gravitational variations governing the cosmos. This application of cold atom interferometry transforms a tool designed for terrestrial navigation into a telescope turned inward on the laws of nature. Scientists at leading research institutions recognize that any device capable of measuring acceleration with absolute quantum precision is inherently capable of testing the foundational theories describing reality itself. The same atomic superposition that keeps a submarine on course without satellite signals now serves as a pristine laboratory for interrogating the universe. Albert Einstein's theory of general relativity posits that gravity warps the flow of time, causing clocks closer to a massive body to tick slower than those further away. Historically, verifying this time dilation required launching atomic clocks into orbit or carrying them up mountains. Today, quantum atomic clocks have achieved such extreme precision that they can measure this relativistic effect across a height difference of mere millimeters. By separating two microscopic clouds of ultra-cold strontium atoms by just a fraction of an inch within a vacuum chamber, physicists observe a measurable difference in their ticking rates. The atoms positioned slightly closer to the center of the Earth experience a stronger gravitational pull, and their quantum state evolves measurably slower. This unprecedented sensitivity validates Einstein's predictions at a microscopic scale and opens a new frontier in geodesy, where the flow of time itself maps the Earth's gravitational field. This extreme sensitivity has initiated a coordinated international effort to detect dark matter, the invisible substance theorized to make up the vast majority of the universe's mass. In recent studies published in journals like Nature, astrophysicists outline plans to deploy a synchronized global network of quantum sensors designed to act as an Earth-sized antenna. As the solar system drifts through the galactic halo, researchers anticipate that waves of dark matter will cause minute, transient disruptions in atomic structures. If a dark matter wave interacts with ordinary matter, it should trigger a tiny, synchronized fluctuation across a globally distributed array of quantum atomic clocks. By comparing timekeeping data from sensors in Colorado, Paris, and Tokyo down to the attosecond, scientists look for a correlated anomaly unexplained by local environmental noise. This procedural shift transforms solitary navigation instruments into a planetary-scale observatory, hunting for the elusive particles that hold galaxies together. Yet the precision that allows humanity to probe the mysteries of dark matter carries an inescapable, sobering weight. The scientific community is acutely aware of the dual-use nature of quantum navigation technology, recognizing that the ability to track a subatomic gravitational shift is identical to the ability to guide a hypersonic missile with absolute unjammable accuracy. The awe of unlocking the universe's deepest secrets is inextricably linked to engineering advanced military assets. Researchers frequently grapple with this ethical tension, knowing their work on cold atom interferometry will inevitably integrate into autonomous weapon systems and stealth submarines. The pristine vacuum chambers of academic laboratories are directly funding the strategic defense initiatives of global superpowers. This creates a complex emotional landscape for physicists who must reconcile their pursuit of pure knowledge with the formidable, potentially destructive applications of their discoveries. To manage the rapid commercial and strategic deployment of these systems, the National Institute of Standards and Technology is drafting rigorous international testing protocols for quantum sensor performance. These standardization frameworks define exactly how a quantum gyroscope must operate under extreme thermal and vibrational stress, establishing a unified baseline that manufacturers must meet before integration into civilian aviation or public infrastructure. The immediate consequence of this intense engineering phase is an economic bottleneck, where the exorbitant cost of manufacturing miniaturized vacuum chambers restricts early adoption. For the foreseeable future, only well-funded state actors, defense contractors, and massive multinational extraction companies will possess the capital required to deploy true quantum inertial navigation systems. However, the relentless drive toward mass production is already setting the stage for a broader societal transformation. As fabrication techniques improve and costs fall, the integration of quantum sensors into commercial logistics promises a future where everyday supply chain workers operate with absolute navigational certainty, insulated from external satellite vulnerabilities. This technological trajectory closely mirrors the historical evolution of the microchip and the original global positioning system, both beginning as classified military projects developed by the Department of Defense before shrinking in size and cost. Just as the first room-sized computers gave way to ubiquitous smartphones, the current generation of bulky, lab-bound quantum sensors represents merely the foundational architecture for a future of integrated quantum measurement. Imagine a fully autonomous digital city of the future, where thousands of driverless vehicles and automated transit networks weave through dense urban canyons in perfect synchronization, completely untethered from the sky. Yet, as this vision of self-contained precision approaches reality, a critical unresolved question remains: whether the global infrastructure built upon decades of shared satellite time can smoothly transition to a decentralized paradigm where every vehicle holds its own absolute truth of space and time. The realization of this decentralized paradigm will trigger a psychological shift in how civilization interacts with its navigational tools. For over a century, from early radio beacons to global positioning system satellites, humanity has relied on external broadcasts to determine its location. Quantum navigation severs that invisible tether, replacing reliance on distant signals with absolute trust in isolated atoms. A maritime captain navigating a signal-jammed strait will no longer look to the sky for guidance, but to a self-contained vacuum chamber in the hull, marking a cultural transition toward complete navigational autonomy. Achieving this autonomy requires acknowledging the monumental engineering hurdles that remain. Researchers at laboratories like the National Institute of Standards and Technology are currently grappling with the physical limits of size, weight, and power reduction, often referred to as SWAP. For the aerospace engineers integrating this technology into commercial aircraft, the immediate aftermath involves difficult compromises. They must balance the extreme accuracy of cold atom interferometry against the reality of outfitting planes with heavy cooling lasers, dictating entirely new design parameters for the next generation of flight. The roadmap for the next decade outlines critical milestones designed to shrink these components into ruggedized modules. Public reporting from research universities suggests the immediate focus centers on developing solid-state laser systems and advanced photonic integrated circuits. This miniaturization effort will create a significant technological aftershock across the broader photonics industry. By forcing the rapid commercialization of microscopic lasers, the quest for quantum navigation is inadvertently accelerating advancements in medical imaging and high-speed telecommunications, proving that tools built to measure gravity will reshape unrelated sectors. This convergence highlights humanity's shifting method of finding its place in the universe. Instead of triangulating a position relative to satellites, we are learning to orient ourselves by interrogating the fabric of space-time, measuring localized distortions of gravity and acceleration. Even as this capability matures, a compelling scientific question remains unsettled: whether quantum sensors will eventually become sensitive enough to detect new gravitational anomalies that classical geology has missed. Data generated by autonomous vehicles could inadvertently map the subterranean Earth with extreme resolution, rewriting our understanding of the planet's internal structure. The transition toward GPS-free quantum navigation stands as a testament to the staggering elegance of applying quantum mechanics to the macroscopic world. By harnessing the superposition of rubidium atoms, scientists are forging a future where global commerce is permanently immunized against external disruption, securing an era of absolute navigational independence. Deep inside a sealed titanium chamber, isolated from the chaotic radio frequency noise of the outside world, a microscopic cloud of rubidium atoms hovers just a fraction of a degree above absolute zero. Struck by precisely tuned laser pulses, these atoms momentarily exist in two places at once, silently registering the faint gravitational pull and rotation of the Earth turning beneath them. It is a quiet, invisible dance of quantum mechanics unfolding in absolute darkness. Yet from this fragile, microscopic suspension of reality, humanity is forging an unbreakable compass. We are building a future where our most vital systems no longer look outward to vulnerable satellite broadcasts for guidance, but instead turn inward, relying on the fundamental, unalterable fabric of the universe itself to chart our way forward.